So the final video that I'm going to make for you tonight is on the ear. So let's take a look at the ear. So we'll go to here, and we'll start the ear right now. So the first thing we have to talk about is sound. So any sound that you hear is based on pressure waves. Just like light waves, sound waves vary in their amplitude and their wavelength. Most sounds are a mixture of different wavelengths, so sounds also vary in their purity or how varied the mix is. The physical property of amplitude affects mainly the perceived quality of loudness. Wavelength is the primary determinant of perceived pitch, and purity is the main determinant of timbre. For the most part, higher frequencies are perceived as having higher pitch. For example, I'll let you hear this in a second. If you strike the key for high C on a piano, it will produce a higher frequency sound wave than the key for low C. So here's how that sounds. High C, higher frequency, higher pitch. Low C, lower frequency and a lower pitch. So now let's talk a little bit about human hearing. So the graph that you're seeing shows the absolute thresholds, if you remember from the first video, for the weakest sounds people can hear at various frequencies. Humans can hear sounds ranging in frequency from a low of about 20 hertz up to about 20,000 hertz. Sounds at either end of this range are harder to hear. The frequencies between 1,000 and 5,000 hertz yield the lowest absolute thresholds because the human ear is most sensitive to sounds in that range. So this is the range that most of us hear the best at, between 1,000 to 5,000 hertz. Well, let's take a look at some of the things that we just talked about. Would you be able to hear a 50 decibel sound at 50 hertz? So here is the decibels, 50, and 50 hertz would be about here. So it's not shaded in, so I'm saying the answer is no. 10 decibels at 1500. So here's 10, and then we go to 1500, and that would put us somewhere in this range over here. So it'd be tough, but some people with good hearing probably could. I'm going to say yes. 40 decibels at 500 hertz. So here's 40 decibels, 500 hertz. That would be yes. Okay. In general, the greater the amplitude of the sound wave, the louder the sound perceived. And amplitude is measured in decibels. So the table that I'm showing you here lists the decibel level for some common sounds. A general rule is that perceived loudness doubles with about every 10 decibel increase in amplitude. So a rocket launching would be 170 decibels, 80 decibels, busy traffic, a noisy restaurant. Usually anything above 90 for too long can lead to hearing loss. So very loud sounds can jeopardize your hearing. As you can see here in this graph, the human threshold for pain hovers around 120 decibels. Even brief exposure to sounds over 120 decibels can be painful and may cause damage to your auditory system. Then the purity or complexity of the sound influence how timbre is perceived. So if you want to better understand timbre, I'm going to show you two different notes with the same loudness and pitch on a French horn. The difference that you perceive is the difference in the timbre. So here's the horn. Here is the violin. Now let's look at how the ear processes sound. Like your eyes, your ears channel energy to the neural tissue that receives it. The human ear can be divided into three sections: the external ear, the middle ear, and the inner ear. Sound is conducted differently in each section. So the external ear consists mainly of the pinna, a sound collecting cone, the outside part of your ear. Sound waves are collected by the pinna and then funneled along the auditory canal towards the eardrum, a taut membrane that vibrates in response. So this is the eardrum here. In the middle ear, the vibrations of the eardrum are transmitted inward by a mechanical chain made up of three of the tiniest bones in your body, and that would be in here. These are the three bones, known as the ossicles. These bones, which are called the hammer, the anvil, and the stirrup, form a three-stage lever system that serves to amplify teeny changes in air pressure. The inner ear consists largely of the cochlea, a fluid-filled coiled tunnel that contains the receptors for hearing. The term cochlea, believe it or not, comes from the Greek word for a spiral-shelled snail, which the chamber resembles. Sound enters the cochlea through the oval window, which is behind and is vibrated by the stirrup, one of those tiny bones. The ear's neural tissue is inside the cochlea. Now let's take a look at what is going on inside the cochlea. So what you're seeing now is a section of the cochlea unwound and cut open to reveal what is called the basilar membrane, which divides the interior of the cochlea into two chambers. The membrane is covered with thousands of tiny hair cells that serve as the auditory receptors. Pressure waves in the fluid in the cochlea causes oscillations to travel in waves down the basilar membrane, stimulating the hair cells to fire. As with the rods and the cones in the eye, the hair cells convert this physical stimulation into streams of neural impulses that are sent to the brain. And I believe that is the end of this video series on the eye and the ear.